board. And let us start off by talking about metabolism. So as you guys have learned, there are two phases of metabolism. Phase 1 metabolism's role is to inactivate the drug, whereas phase 2's role is to get the drug out of the body. Now, normally the role of phase 1 is to add some sort of very, very, very polar group or remove some sort of polar group, right? Um, and but the fact of the matter is that doing those processes inactivates the drug, and that's the big thing. We make some sort of modification in order to prevent it from fitting into the receptor, and then we use phase 2 to get rid of it. The goal of phase 1 really is about those polar groups. So to summarize that, phase 1, you are going to make a polar group. So what is a polar group? These are things like OH, SH, or NH bonds. And phase 2 is all about conjugation for elimination. So in phase 1, we have inactivation of the drug. Whereas in phase 2, we increase the solubility in water, aka increase hydrophilicity. Why do we want to increase hydrophilicity? What is the purpose of doing that to a drug?
Be able to excrete it?
Exactly. We need to pee out the drug. The kidney, the urine is one of the primary ways that we get rid of substances. So it makes sense that we just make it super, super hydrophilic. So it dissolves in the water, in the urine, and just pee it out in the filtrate. All right. So let's talk about these different concepts in this. And what I'm going to do is I'm primarily going to focus on the drugs that you guys have to know. So there's a list of drugs that he put online that you should know about the metabolisms for. All right. No? Oh. There we go. So here we have, actually, does anyone know, can anyone identify this drug for me?
Is that naproxen?
It is naproxen. Very nice. Do you have to be able to identify drugs on this exam?
I don't think so, no.
Okay, all right. Then that is the end of those questions. On all other exams, you will have to. But you're that's primarily going to be the only thing that you're doing on these exams, and it's really not that bad as people think. All right. Phase 1. The first kind of phase 1 metabolism that we have is hydroxylation. The purpose of hydroxylation is to add an OH. And there are two kinds of hydroxylation that we can find. There is aromatic hydroxylation, and there is aliphatic hydroxylation. Aromatic hydroxylation is pretty straightforward, where we are going to add an OH para to the drug. In some sort of para position. So, for example, if I just move that down, if we had a drug that had a benzene ring and we had some sort of big complicated R group over here, then what we have is the ortho, meta, and then para position. And so we would be adding an OH group primarily in the para position. Now, if we look in naproxen, for example, we have this methoxy group, this ether, and para to the methoxy group is occupied. So can it insert an OH here? No. How do you identify the para position? It's always relative to whatever else is going on. But in general, para can exist to any group that's already there. So what would be para to the methoxy group? This carbon. Maybe that blue is too hard to see. What would be para here? Right there. But what's para to this connection? Over here. So you can see that para can be a relative thing, right? So could I put an OH coming off of this position here? 100%. It's just that if you had to choose between para positioning and ortho or meta positioning, it's always going to choose para first. Para is faster, para is better. So if you have the choice between ortho, meta, and para, choose para. And that is the second point that we want to put here. If para is occupied, then ortho or meta are chosen next.
Good
Now,
question.
yes. What's your question?
Sorry.
Okay.
So if any drug has a benzene ring, would it automatically undergo the aromatic hydroxylation or no?
100%. As long as it has open carbons on that benzene ring, there's always a possibility of aromatic hydroxylation.
Okay.
Good question.
Question 2. He never actually talked to us. How would we choose what is the metabolic reaction we're going through, like priority wise? So whenever he asks about what reactions this may go to, should we just pick everything that may be possible?
So hold that question for just a second, because I'm going to show you an example of when we're choosing like best pathways and stuff like that.
Right.
For aliphatic hydroxylation, what we are talking about here are carbon chains. specifically for this, you need to have a carbon chain larger than 2 carbons in a row. Correct. It is preferred to put hydroxyl para to the heteroatom. So what that means is, let's say we had a pyridine. The preferred position would be here. Aliphatic hydroxylation, you need to have a carbon chain that is greater than 2 carbons. So an ethyl group is not a valid position for We'll talk about that in a second, Jana. Good question. So in aliphatic hydroxylation, the rule is that the last carbon is preferred if the last carbon is occupied, then we denote this with the Greek letter I think what is that? Delta? Gamma?
I think it's omega. I don't know.
Might be omega. Yes, omega. With the Greek letter omega is the last carbon. If it's occupied, then if occupied, choose omega -1. So if you have a 5 carbon long chain and the 5th one is occupied, then it would choose the 4th one and then the 3rd, and so on and so forth. The last point that we want to make about aliphatic hydroxylation, and this is the big thing about aliphatic, is the longer the chain, or more branched, the increased chance of aliphatic hydroxylation. And that should make sense, right? If you have a 100 carbon long tail, that is a juicy place to put an OH. So the bigger the chain, the faster the reaction, and the more likely it will occur. So when we talk about what I want to, let's talk about barbiturates real quick. And we'll go back to naproxen in a second. Except for thiopental, we're not going to talk about that. What kinds of metabolisms would we expect for pentobarbital? So let me label some carbons for us. A, B, C, D, G, H. Exactly. Pentobarbital would go through aliphatic hydroxylation. What carbon would we expect the OH to appear on? Yeah, carbon H. Why? Because it is at the end of the chain and it's the longest possible chain. What would be the next preferred carbon? So let's say that there was a tert butyl group coming off of H. So it's fully occupied where something is connected to this where this isn't valid anymore. Exactly. G would be next. What would be after G? F. There you go. Now you get it. Would carbon C ever be chosen? Would carbon C ever be chosen?
No.
Exactly. No, it is too short. Remember the rule. The carbon chain must be greater than 2 carbons, and we can see that that chain is only 2 carbons long. So what we find is that if you just have 2 carbons here, you have no aliphatic ability to hydroxylize it, right? So in terms of aliphatic hydroxylation, this ethyl group is mute. All right. So no, too short. All right, let's talk about phenobarbital. For phenobarbital, what kind of metabolism is it going to go through? Aromatic. Yeah. Can it go through aliphatic hydroxylation?
No.
No. Once again, that carbon chain is too short. In terms of aliphatic hydroxylation, it is invisible. It does not exist. What is the preferred carbon for metabolism of phenobarbital? Carbon 7. Yeah. Why? Because it's para to the drug. If it can't go through carbon 7, which carbons will it choose next? Yeah. For all you guys have to know, it's going to choose 5, 6, 8, or 9. You don't have to determine which one is better. You just need to know that it is the non-preferred carbon. That's all it is. So what kinds of things do you need to be able to do when you see just one drug structure? So we're not talking about 2 drug structures. We're not talking about comparing anything. What you need to do is you need to be able to identify what are the possible reactions and what carbon would that reaction prefer to happen on. Does that make sense? Any questions about that? All right, let's go back to, actually, right before we do, I want to throw in another drug. So this is called barbital. For barbital, whoops. What would be the preferred of our 2 hydroxylations? Which one would be preferred? Aromatic, aliphatic. Answer is neither aromatic or aliphatic. This is a trick question. Can it undergo aromatic hydroxylation? Is this a aromatic ring? Do we have benzene? Do we have double bonds creating?
Nope.
Exactly. This is not aromatic. So we do not have an aromatic ring. And why can it not go through aliphatic hydroxylation?
So the ethyl groups.
Exactly. Ethyl is too short for aliphatic hydroxylation. It is invisible to aliphatic hydroxylation. Exactly. Methyl and ethyl. Exactly. Yep. Yep. So here's the last question. Who has, of these three drugs, pentobarbital, phenobarbital, and regular old barbital, who has the longest half-life? So the half-life is a function of how many active places can we create the phase 1 metabolism. I believe you need to be able to talk about comparing structures. You need to talk about longest or shortest. I think that is something. Did he talk about half-life in the packet? I can't remember. A bit. Okay. We'll cover it just to get all of our bases covered, but I don't think it's something we have to focus too much on. So the answer here would be barbital. Why? To have a long half-life means to have few places for metabolism. So pentobarbital can be metabolized by aliphatic, phenobarbital can be metabolized by aromatic, but barbital has neither of them. So which one of them would hang around longest in the body? It would be barbital, because it cannot undergo those two kinds of metabolisms. Does that make sense? Any questions about this? Is there a preference for longer half-life of aliphatic over aromatic? There is some things that determine it, but you don't have to know it for this exam. You will learn it on later exams. All right, let's keep moving along. Dealkylation. An alkyl group is just a carbon chain. That's all it is. So when we talk about dealkylation, what we are talking about is the removal of a carbon chain from a heteroatom. So we're talking about oxygen, nitrogen, or sulfur. Although you guys haven't talked a lot about sulfur. It's also sort of rare in drugs. The purpose of dealkylization is to expose at least one OH, SH, or NH bond. Why? Because then it can undergo phase 2 metabolism. That's all dealkylization does. It takes some sort of what am I trying to say here? It takes some sort of bonded up heteroatom, exposes it so that way it can directly go to phase 2 metabolism. So here we have imipramine. What we can see here is that we have 2 nitrogens. So either one of these nitrogens could undergo dealkylization. The problem is that really this process can only occur on carbon chains smaller than 4 carbons and preferably unbranched. So we're looking for simple carbon chains. That's it. So a methyl group, an ethyl group, isopropyl, regular propyl, maybe isopropyl. But really, once you start getting really complicated with these alkyl groups, it does not do very well. So when we look at these 2 different nitrogens, what we can say is that which one of these is more likely to undergo dealkylization? Probably the one on the bottom. Why? Because it has much less complicated alkyl groups to remove. And so what we would label this as N-demethylation. So what is the atom that we are removing it from, and what is the group that is being removed? So N-demethylation is a valid metabolism pathway of imipramine. What are other valid metabolism pathways for imipramine? What do we think? Other valid metabolism pathways for imipramine?
Aliphatic?
Not aliphatic. Just like people said, aromatic. Yeah. Why? Because we have these nice big benzene rings, right? So let me label some carbons for you. So for aromatic hydroxylation, what would be the preferred carbon on the numbered benzene ring. So in this one on the right. Yeah, I'd say 3. Why? Because 3 is ortho to 6, or it could be 2. 3 or 2. What about on the left hand? What would it be for the left hand benzene ring? Exactly, E or F. Why? Because either one of them is aromatic. Why not aliphatic? Why can't we metabolize this carbon chain? It's 3 carbons long. It's not open. Yeah, remember, we hydroxylize the terminal carbon, right? The last carbon. Are either one of these the last carbon in the chain or the last atom in the chain? No. So you have something coming after which would prevent aliphatic hydroxylation. What about these 2 carbons up here, however? Could you do aliphatic hydroxylation of those 2 carbons? No, right? Why? Because you have only 2 carbons long. What if it was 3 carbons long or 4? Yeah, you could do it then. Is it likely to do it? No, because a ring is not a terminal position, right? Needs to be a terminal carbon. So just to show you how this all works out, here is the actual metabolism of imipramine. And what we see is that the preferred pathway of metabolizing imipramine is through demethylation, and the secondary pathway is through hydroxylation. Will you ever get 2 OHs? Can I ever have a metabolism where it says, yeah, I'll put an OH on both sides? No, exactly. It's only going to go through one pathway. It's only going to do it once, right? It's going to do one of each reaction. So it does one hydroxylation, one demethylation. It's not going to go, oh yeah, let me hydroxylize it and hydroxylize it again, because otherwise it would just stick OHs all over this thing and then it would be able to dissolve on its own. That's not the role. The role of phase 1 is to add one group of one reaction. That's it. Because as soon as that happens, now we can attach it to some sort of phase 2 reaction and we're on our way. That's all it cares about. Any questions about this business? Is this making sense so far? Is this helpful for people, or am I just like going over things they already know? Okay. Let's go back to naproxen then. What are all the valid metabolism pathways of naproxen? So let me do some labeling here. So what are some valid ones? I see aromatic hydroxylation. I see an O demethylation. One more. Valid metabolism pathways of naproxen. Dealkylation, yep, through O-demethylation, totally. Don't forget, if you already have an OH, NH, or SH bond, you can do direct phase 2 metabolism, right? If you already have an OH, SH, or NH, you can go right to phase 2. You don't have to go through phase 1. So don't forget that one of the valid pathways of any drug is always directly skipping phase 1. And so, if we look at the metabolism pathways of naproxen, exactly, because it already has an exposed OH bond. So it can go through directly because it already has an OH, NH, or SH bond. If you already have one of those, you are good to go. So if we look, naproxen, one of the things that can go through is O-demethylation, which it then directly conjugates either through sulfation or glucuronidation, or it can just directly do it, right? Because it has that nice exposed OH and it can conjugate directly. So either it takes advantage of the pathway through O-demethylation, or it just does glucuronidation directly. So direct to phase 2 is always a valid metabolism. All right. Continuing on our way. Oxidative deamination. As far as you are aware right now, they are all equal to each other. You don't need to know, you don't need to be able to talk about like preferred or, major metabolite, anything like that. And if he does, the answer is very, very, very clear. And I will show you an example of that where we talk about preferences and stuff. All right. Oxidative deamination. What we are talking about here is the removal of a primary amine into an aldehyde. And technically a ketone as well. I don't think I don't think it is technically. I think it is literally an aldehyde or ketone. So if I need to pick a drug, what's a drug that has what are some tricyclic? Do, do, do. Amphetamine is one of them. I want to give an actual drug rather than, but I guess it's mostly What a shame. Let me do this. Do. And I do. Nope. So we'll go back to this drug. So this is a made-up drug, similar to imipramine, but it does not exist. And so what we are looking for with a drug like this is a terminal NH2 group. So things you need to look for oxidative deamination is you need to see NH2 and the carbon connected to the NH2 is not substituted. So what do I mean by that? What I mean is that let's say that we had this drug where it had two NH2 groups. Either one of these could undergo oxidative deamination. Either one of them is perfectly valid. The result would be where we either have an aldehyde on that terminal carbon, and that NH2 would still be here, or we still have our original NH2, and now we have a ketone. So if you're, not really sure how to do this, and it's kind of like sticking in your mind, you're not sure, the rule of thumb is put a dot on the carbon that the primary amine is connected to, and convert this into C double bonded O. So I'll do this in a darker color. Convert it into C double bonded O. That's all you need to do. Put a dot on the carbon it was originally connected to, and do C double bonded O. Big brain, right? So we said earlier that the purpose of phase 1 metabolism is to create a very polar group, right? Phase 2 metabolism produces an OH on a specific portion of the drug, so that way it's easier to metabolize, to get rid of, to go through phase 2 metabolism and remove from the body, right? Make a polar group, OH, SH, or NH bond. Oxidative deamination does not do that. It does not produce a very polar group. In fact, it takes away a very polar group, right? It takes away NH2. So what is the purpose of oxidative deamination if it's doing the reverse of what we think oxidative deamination would do? What is the purpose of oxidative deamination? Yeah, Get rid of the NH2, inactivate it. Remember that one of the big functions of phase 1 is an activation of the drug. So that NH2 group must have some big action for the drug. So oxidative deamination is all about getting rid of the action. Get rid of it. We can do a different phase 1 later, but right now we need to inactivate the drug. And often drugs that have to go through oxidative deamination are some of the ones that are the harshest on the liver. Oh no, is that true? No. I think the better way of saying this is that the drugs that have to go through oxidative deamination are some of the most potent drugs out there. Things like amphetamines, norepinephrine, epinephrine, all those sorts of things. Any questions about these 4 reactions that we went through?
Yes, I have a quick one. So for oxidative deamination, Mahana didn't really go into specifics about the ketone portion. So all he specified that it had to be like a secondary carbon this is a really dumb question. Is when you drew on the NH2 originally, sorry, hold on, that you didn't have, yeah, that one. Would that be still considered a secondary carbon?
Yes, this is the secondary carbon, which would produce the ketone.
Okay, thanks.
So essentially what it is that if your NH2 is in the middle of a chain, you'll get a ketone out of it. If it's at the end of a chain, you'll get an aldehyde out of it.
Alrighty.
Yes, oxidative deamination is the only phase 1 reaction that gets rid of a polar group. It's the only one. Is that true? I believe that's true. All right. So what we have just talked about are all of the microsomal reactions. Microsomes are vesicles that are part of the endoplasmic reticulum, and in the liver, hepatocytes contain a very, very, very large endoplasmic reticulum, and part of that is that they have tons and tons of enzymes in them. So we call the reactions that primarily happen in the liver microsomal. So these would be the hydroxylations, the dealkylizations, let's try spelling it correctly. And oxidative deamination. So these are all happening in the liver. The other kind of reactions that we have are called non-microsomal. And these are essentially just general reactions that happen outside of the liver. So could they happen in the liver? 100%. But do they occur in other places? Yes. And in fact, you're more common to find these in places like nerves, the lung, the GI tract, plasma, and the liver. So microsomal reactions, liver only, non-microsomal, many, many other places. There are 4 non-microsomal. You have monoamine oxidase, MAO. You have catechol O-methyltransferase. COMT, amidase, and esterase. We're going to talk about the amidase and the esterase first, just because they're incredibly common in the body. Super, super, super common. And they are something that we take advantage of in the creation of prodrugs. So let's talk about the last 2 first. So esterase. The function of esterase is to take an ester here's our nice ester, and we are going to cleave it apart at the ester bond. So what is going to come out of this is that we are going to cleave it apart right there, cut it in half, and what we are going to be left with is the carbonyl portion and an alcohol portion. So we are left with a carboxylic acid and an alcohol. What molecule is required for an esterase to do its job? What molecule is required?
Water.
Water. Yeah, we need H2O, which can also be written as HOH. Is there water found in the body?
Yes.
Yeah, right? Not a trick question, right? Tons and tons of water in the body. So are esterases pretty much able to function anywhere they want? Yeah, they can pretty much function anywhere. Things to know about esterases is that it is a very fast reaction. Incredibly fast. In fact, it is one of the, I think it is the fastest metabolic reaction of them all. So if an ester is on a drug, you can almost guarantee it is being destroyed. If an ester is present, it will be destroyed. So let's take a look at an example here. I need a morphinium. Oh, duh. All right, so let me grab this structure. Does anyone know what this structure is, by any chance?
Naloxone.
You're not far off. It's morphine. It is morphine. Very nice. If we look at morphine, well, let's actually list them out. So what are the metabolic pathways of morphine? Aromatic hydroxylation. Totally. So we could put an OH here. We could put one here. Totally. And demethylation. Yep, that is a valid one. One more. Straight to phase 2. Exactly. Direct phase 2. Why? Yes. So dealkylation is the general broad term for any kind of removal of a chain. So demethylation is just a type of dealkylation. Good question. So morphine is able to directly go through phase 2 metabolism. So let's take a look at a similar structure, a modification of morphine. You know what I'm gonna do? There we go. Fine. So here's morphine. And what do you notice that they did to our OH groups that were on our benzene rings? Crab spider. What do you notice that they did? They turned them into esters. Exactly. So here we can see an ester bond. What is the purpose of adding esters to a drug? What would be the purpose? Making it easier to metabolize. Well, do we ever really want a drug to metabolize? No, right? We would like a drug to just hang around as long as possible, right? So is this drug, first of all, this mystery drug, is it going to undergo direct phase 2?
No.
No, it's not. But what do we know about esterases? It's a super, super fast reaction. It can happen anywhere in the body, right? So are these acetyl groups which is what they are, they're acetyl groups, are, which again is a type of ester, are these hanging around on this structure very long once it's absorbed into the body? Are they going to hang around very long? In other words, we have tons of esterase in the blood. Are those esters going to hang on very, very long? No. So one of the functions, so why have this group if it's just going to get removed very quickly and then we can go directly through phase 2? The reason is, and I saw someone say it earlier, is that adding esters improves what? What is going to improve about adding these ester groups? Exactly, lipophilicity. We take this very, very polar group and we turn it into a non-polar group or less polar. So instead of this highly, highly polar OH bond, we now turn it into an ester. So we have our ester prodrug, have this get absorbed, and then we have our esterase liberate the active drug. So in terms of creating drugs, in terms of thinking about how drugs are created, why do we add esters to drugs? To increase the absorption, knowing that those ester groups are going to get removed very, very, very quickly. Does that make sense? So on the exam, what are you going to be asked about esters? Obviously, they're going to ask about metabolism, right? They're going to say, what's a valid metabolism of this mystery drug? And you'd say esterase. But what is the function of adding ester groups? Increase lipophilicity to make absorption better. Does anyone know what this mystery drug is? Anyone by any chance? It will tell you it's the prodrug to morphine. It's more potent. Codeine is close. Codeine's a good guess. Opium's also a good guess. This is heroin. So why is heroin a more potent drug? Why do you need such a smaller dose of heroin than you do of morphine in order to overdose? Because it is absorbed so much easier into the body. So potency is also a function of absorption. So you acetylize, you add esters to morphine, you get heroin, and now you need less drug in order to get into the body to, metabolize into the active drug. Any questions about what we just discussed? All right. All right. Let's talk about the next one. No. Adding, so for heroin, adding esters to make a prodrug this increases lipophilicity, which then increases absorption, which means smaller dose. So it doesn't change anything. Would this change efficacy at all of morphine, of the active drug? No. Doesn't change efficacy at all. It just changes potency, right? Because it's better at absorbing. All right. Amidase. Very, very, very similar to an esterase is amidase. Amidase is where you are going to be taking some sort of amide functional group, you are going to run it through this enzyme. And once again, you are going to cleave this bond in between the carbonyl and the nitrogen. Except this time, what you are left with is a carboxylic acid and a primary amine. So you have a carboxylic acid and a primary amine. Uh, Some things about amidase. It is a slower reaction than esterase. Slower reaction than esterase. So let's say, for instance, I had a drug that was like this. Which bond is more likely to be metabolized first? Which
A.
A, right? Why? Because esterase is a much, much faster reaction. So we have an ester bond here. And we have an amide bond here. So who has the faster reaction? It would be the ester. So let's put this in context of real drugs. Oop, that is impossible to see. Here is a drug called lidocaine. What are all the possible metabolic pathways for lidocaine? What are all the possible metabolic pathways for lidocaine? Aromatic hydroxylation, totally. Put that OH right there. I see ND, what would it be? We have 2 carbons, so this would be ND ethylation. Very nice. What else? Can we go direct to phase 2? No. And this is where I want to talk more specifically about this amide bond. When we talk about phase 2, what we are specifically looking for are things like NH2 or even NH, where, maybe it has, this is a better way of explaining it, where we have NH2, maybe we have it connected to another bond, or we have OH. What's important to note about these is that this is an amine. Here we have an amine. And here we have a hydroxyl group. Is the NH in lidocaine an amine? No. It is part of the amide functional group. So can this NH undergo phase 2 directly? No. So there's no direct phase 2 because this NH is not an amine. It is an amide. Why? Because it is conjugated with the carbonyl. So what is the last kind of reaction that our lidocaine can go through that we just talked about? Amidase. Exactly. So if you ever see an amide bond, is amidase a valid metabolic pathway? Yes. If you see an ester, is esterase a valid metabolic pathway? Yes. All the time. Totally. Let's talk about a very, very, very similar drug called dibucane. Not dibucane. I want to talk about not lidocaine, not procanamide. No, that's an amide. Ester, local anesthetics. Provocaine. Not provocaine, but we could do procaine. That's a good idea. Or actually, it's kind of complicated. We won't do that. We'll do procaine. All right. Here we have a drug called procaine. And focusing specifically on the ester and the amide, which would have a longer half-life? Lidocaine or procaine? Which one would have a longer half-life? Or in other words, which one is going to metabolize slower? Some people saying lidocaine, some people saying procaine. Well, we know that lidocaine is going to go through amidase. And we learned earlier that procaine is going to go through esterase. So which is the faster reaction, amidase or esterase? Esterase is faster, so that means lidocaine must be longer. So how do we arrive here? We know that lidocaine is an amide. Amidase is a slower reaction than esterase, which means that it will metabolize slower. Any questions about that? All right. Let's talk about one more drug, and then we will wrap up on amidase. And bang. Oh, wait, do I want this one? Um, yeah, we could talk. That's valid enough. All right. Here we have a made-up drug, similar to valproic acid. What are the valid metabolic pathways for this drug? If you want to have a drug stay in the body longer, wouldn't you want to add an amide or ester because it is metabolized slower? That is a part of it. Yep. So you can add esters and amides, which would increase metabolism, decrease metabolism because, you're hiding those OH, NH bonds. Totally. But also too, that the real function of adding those amides or esters is to help with absorption. So we have aliphatic, I would agree, 100%. Look at those nice big chains. Some people are saying amidase. And we have direct phase 2. This is where the complicated part about amidase comes in. Amidase requires that this nitrogen have at least some sort of carbon chain coming off of it. Amidase is not able to work on amides, which this is an amide, where that nitrogen does not have any carbon coming off of it. It does not operate very well. Actually, no. No. I'm completely wrong. Amidase is a valid option here. I'm completely wrong. Disregard what I just said. It's an amide, it goes through amidase. My bad. My bad. It's an amide, it goes through amidase. Yeah, no kidding, right? All right, let's go on to the next one. Catechol O-methyltransferase. What I don't really get about the way that this was taught is that he didn't tell you what catechol is. Catechol is a benzene ring that has two OH groups next to each other. So if you have this catechol group in your drug, you are able to go through CompT. What the function of CompT is it is that it takes a drug and it wants to inactivate this catechol portion. Let me see if we can get a good picture. Not really. So let's take a look at dopamine. What CompT does is that it will add, CompT will add a methyl group onto the carbon 3 OH group. Which one is the carbon 3 OH group? It is the non-para. So the way that we number catechol is we put 1 at the group that's coming off of catechol, and we number around towards the first or the closest OH group. So what CompT is going to do is it's going to add a methyl group onto that OH. The function of CompT is to prevent catechol function. Which is basically saying that we're going to inactivate a whole bunch of neurotransmitters. Lots of neurotransmitters have this catechol functional group in them. And so by going through COMT, what we are doing is we are preventing them from binding into the different receptors. So alpha, beta, dopamine, histamine, all those good ones. Histamine? Pretty sure it's histamine. The other one that has a very, very, very similar effect to this that often occurs in the same place that COMT occurs is monoamine oxidase, or MAO. This is not MAO, it is MAO. Please do not call it MAO. So monoamine oxidase is going to remove MAO. A terminal amine, specifically a primary amine. So we see something like NH2. And this is going to create an aldehyde. So we can use our structure here, and we can say that one of the other metabolic pathways, which, by the way, this is dopamine. One of the other metabolic pathways of dopamine is through MAO, which instead of affecting the catechol moiety, it is going to work on that terminal amine and turn it into an aldehyde.
Question.
Yes.
So I think this is actually what I meant earlier and I messed it up. When you went over sorry, let me zoom out of my notes and like scroll for a second. When you went over oxidative deamination, I think the one on the bottom, I think that was that supposed to undergo MAO instead because it was terminal?
So oxidative deamination can occur on either a primary or a secondary amine. So it could occur on an amine that is here, for an example. MAO can only occur on the terminal one. Does that make sense?
Yeah.
Does
I
his
think
does
it
his book
just-
say
it just says remove an NH2 group connected to a secondary carbon atom cannot be a primary or tertiary carbon. It doesn't say anything else.
oh, okay, my mistake. So then he's saying that so MAO will occur on the terminal and oxidative deamination is on the internal one. So it would not this structure. So only on this position. I'll clear this up later. Don't worry.
Thanks.
I will clear that up later. We're going to look at a couple of examples. For now, just know that MAO definitely works on this terminal position. All right. Let's look at a drug. All right. Here we have the drug quercetin. And what I want you to tell me is what are all the valid metabolic pathways? I see some COMTs. I would agree. What we can see here is that this is the catechol functional group. I see direct phase 2. I would agree. I see esterase. No, yeah, it looks like there's an ester here, but this is just a ketone. Aromatic hydroxylation. Yep. Definitely could put an OH right there if we wanted. And I think that is everything we have. So of these three, COMT, aromatic hydroxylation, and directly to phase 2, which do we think is most likely going to happen first? What is the pathway that this thing is probably going to be removed from the body as? Exactly. Direct to phase 2. If you can skip phase 1, it's going to skip phase 1. If it doesn't have to spend energy modifying the structure of this thing, it will just go and do it. It does not care. If it can just conjugate it somehow and get rid of it, it would much prefer to do that. Any questions about that? Okay. All right. Let's look at let us look at no, let's keep no, we should keep moving on. All right. Any questions about metabolism overall? Before we dive into some practice and I explain that whole business about MAO versus whatever.
I have a really quick question.
Yes.
So this is a stupid question, but if all of the para position, if all the positions on the ring were taken, you couldn't do aromatic hydroxylation, right?
Correct. Yeah. Yep. So if we look at the catechol here, could this undergo aromatic hydroxylation? Yeah, technically you could put an OH here. Is it likely to do it? Not really, because you already have one in the para position and you have one in the meta position over here, but it's still possible. And then of course we have the para position open over here, so that is a valid option. Does that answer your question, Kaylee? Okay. All right, I want to quickly talk about phase 2, and then we'll take a look at practice problems. And then I do want to talk about ionization. We might run over a little bit. We'll see. All right, phase 2. as we said earlier, the function of phase 2 is to get rid of the drug, remove it from the body by conjugating it with a very water-soluble molecule. Conjugation with water-soluble molecule. You guys don't really, you're not going to be quizzed on, which, what the, how can I explain this? You guys are not going to, be asked, of the phase 2 metabolism pathways, which one will occur on this molecule? There's a lot more that goes on in terms of which molecule will get conjugated than what you guys are required to know. But what is important to know is that there are multiple different kinds of molecules, and they all function slightly differently. The top one, and the one that you should always be aware of what it looks like and be able to pick it out of a crowd, is glucuronic acid. Glucuronic acid. Glucuronic acid is the oxidized glucuronic acid is the oxidized form of glucose. Glucuronic acid. Glucuronic acid is very, very, very water soluble. You stick one of these things onto a drug and you are going to help it get out of the body super, super easily. And part of that is because of all the different OH groups that are on glucose. The other ones that we should be aware of is sulfation, which is where we are adding a sulfonyl group, which often you will just see as SO3. Glycine, which, let me get a good picture of glycine. It's easier just to draw. There's glycine. And the last one is glutathione. I believe there's another one as well. I think UDGP. So here we have glutathione. You should be able to see any of these structures. Yes, all 4 of them. They all have an ability to make a drug very water soluble. Very, very, very water soluble. So you stick one of these on a drug, it is going to dissolve in water much more easily. Glucuronic acid is the preferred molecule. And so more often than not, glucuronic acid, glucuronidation is going to be the one that's used. But that being said, you should be able to identify these other structures And so if you see a molecule that has glycine on it, you should be able to say, oh yeah, that underwent phase 2 via glycination. Same thing, if you see glutathione, it's not so important to understand, which are the different amino acids of glutathione. It's more important to just generally look at this and say, okay, that's glutathione. It's making it much more water soluble to get rid of the drug. One of the things that ends up happening is that glucuronic acid is really, really hard to store in the liver. So the way that it ends up getting stored is as this UDP-GA. UDP-GA. And essentially what happens is that this portion of the molecule, the UDP portion, is going to get kicked off in order to have the drug preferably connect to glucuronic acid. So what do these reactions look like? What you will be expected to, on the exam, to do is is that you will be given a metabolism of drug. So here, I can make this a little bit bigger. You'll be given the structure of a drug. I don't have room. And you'll be expected to be able to identify what the different conjugates are on that drug. So we don't have to worry about this one. Right? Yeah. No, I was wrong. That is a valid one. So as we can see here with acetaminophen or paracetamol, one of the potential pathways is through glucuronidation. And you can see that we have that glucuronic acid connected here. You can identify glucuronic acid because of all these nice oxygens on it. It's also a 6-membered ring. Here we have glutathione. And then the last one we have here is the sulfate. So on the exam, what you're going to be asked about is, what was the conjugate that was added to the structure? Or what is the purpose of adding this structure, this molecule, to the drug? And the purpose would be to enhance excretion. Any questions about that? All right. Let's take a look at one last structure, talk about its metabolism, clear up that mistake I made earlier. All right. Here we have a drug called lisdexamphetamine. Also known as Vyvanse. Some people are clearly excited about Vyvanse. What are some valid metabolic pathways for this? And what I want you to specifically do is I want you to tell me what carbon they would occur on. So I'm just going to label some carbons for us. 7, 8, 9, 10. Your amphetamine of choice. Good to know. So we have amidase, someone says. What else? What are pathways? And I realize that some people might be drawing the drug. Aromatic. Hydroxylation. Let me give myself some room. I saw an MAO. Oxidative deamination. I see a direct phase 2. I see an aliphatic. Dealkylation potentially. So you mean like a demethylation? I think that's quite literally all of them, all of the pathways. So let's talk through them. So do we have a mid present in this structure? We do. It is this guy right here. And so what we would have is a cleavage between position 10 and position 11. So between C10, between N10 and C11. I think that's totally valid. We have aromatic hydroxylation. And what would be the preferred carbon for aromatic hydroxylation? C1. Yeah. Why? Because it is the para position. Could it go on C6, 2, 3, or 5? Yeah, it's possible. But since we have the para position open, it would only be carbon 1. So on the exam, if you had one structure that had it at carbon 1, and then you had a different structure that put it at carbon 5, and it said, choose the major aromatic hydroxylation, then it would, of course, be 1. Someone asked, can you have both aromatic and aliphatic hydroxylation occur on a structure? Yes, one would occur after the other, but you can't have multiple aromatic hydroxylations or multiple aliphatic hydroxylations. You're only going to get one of each. So one of every reaction is possible. But again, remember that the body is only really going to do one phase 1 reaction and then do phase 2. So it's only really going to do one thing and then try to get rid of it. How about MAO? Where would MAO happen? Yeah. So MAO, just to clarify, MAO is only on terminal amines. So the terminal amine in this case would be N18. Oxidative deamination, this is internal amines, which in this case would be N14. So MAO is terminal, oxidative deamination is internal. Does that make sense? Does that clarify earlier? Okay, sweet. Direct phase 2. Can Vyvanse go directly to phase 2? Does it have an open OH, NH, or SH bond? Yes, it does. It could go through carbon 18. It could go through carbon 14. So totally. Not carbon. It could go through N14 or N18. Very valid. Aliphatic hydroxylation. Where would it go for aliphatic hydroxylation? Well, exactly. It's not possible. Remember that aliphatic hydroxylation has to be a terminal carbon chain, right? So we're talking about a chain that comes down on its own, not the fact that it just has a carbon chain. So because remember, where does aliphatic hydroxylation prefer? That terminal carbon. There's no terminal carbon on the structure in order for it to exist. There's a good bit of explanation there. And then finally, what about demethylation? This carbon 9. Can carbon 9 be removed through demethylation? And then for this one, remember that demethylation is removing a carbon chain from a heteroatom. And the hint here is that how do we normally label demethylation? We say O demethylation, or we say N demethylation, right? So we need to remove it from some sort of heteroatom. Okay. Do we want to do another one, or do we want to move on to percent ionization? Because I know that's something that people are questioning. Another one? Okay. No, I don't want to talk about that. Carbamazepine has a special one, so we could do what could we do? Mm. I want to find a drug that has yeah. This could work. All right. Here we have the drug nifazodone, which is an antidepressant that is unique in which it doesn't have much sexual dysfunction associated with it, mostly because it occurs through 5-HT2A antagonism, or at least that's how it's thought to occur. So what are some major metabolic pathways, or just all of them? We'll talk through all of them. I see aromatic hydroxylation. Definitely agree. We can have an OH being put here. We could have an OH put over here. Jana is incredibly excited about aromatic hydroxylation. What else can we have? Dealkylation. Oh, you know what? I didn't label any carbons for us. Did I? Any positions? 1, 8, 9, 10, 11, 12, 14, 15, 14, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, and I'm putting 26 on the chlorine. All right, what do we think? What can we have? Some people are saying we can do deethylation. So in order to talk about dealkylization, you need to tell me what atom we're removing it from. So is it O deethylation, N deethylation? What kind is it? N? So it's a good question. So we can identify that we have this ethyl group here, but is this ethyl group bonded to a nitrogen directly? No. So in this case, N-demethylation is not possible, but if we had it over here, it totally would be. So it needs to be directly connected to the group. Can we do dealkylization between carbons 9 and 10? Can we just cleave off carbon 9? No. How come? It's way too complicated. So even though that this is 3 carbons long, it's still a huge group, right? So even though that this thing is, can we, even though this is 3 carbons long, we have this massive group here. So at least for here, we don't have no ND alkyl, right? Can we, however, do amidase between nitrogen 10 and carbon 16? Is that valid? Yeah, totally valid. Can we do amidase between nitrogen 15 and carbon 16? Answer is yes. So this is a special kind of amide called a carbamate. It's basically a double amide. And it can undergo amidase both on the left and on the right. So if you see that carbonyl, that carbon double bonded to an O with a nitrogen on it, amidase is always a valid target for all intents and purposes. Other things on here. So we talked about, we could have an OH here, have an OH over here. Can we get rid of this chlorine at all? Is this able to be removed? Yeah. So this is something that I just want to point out, that you cannot remove halogens. I think it's one thing that students get nervous on the MedChem exams. And so one of the fake pathways that they will list is, getting rid of the chlorine. We can't get rid of chlorines or fluorines or iodines. We don't know how to do that in terms of this exam. So it is not a valid pathway. So if you see something trying to remove a halogen, that's wrong. All right. So this one is kind of a opposite question, where this one had tons and tons of different metabolic pathways. This one only really had 2, aromatic and amidase. On the exam, the way that this would look is either multiple choice. So, click all the ones that are valid, or it could be, it could be like choose the correct statements, and then you choose 1 and 3, however they do it. But hopefully that makes sense. All right. Let's quickly talk about percent ionization, and then we'll wrap up, and then we'll meet for tomorrow. I don't mind spending some more time with percent ionization, but I do want to talk about it now, so that way you guys have time to practice it instead of just saying, "Oh, we'll do it tomorrow." It's kind of a waste of your Sunday. All right. Percent ionization, which is also talking about pKa and pH and all that business. When we talk about percent ionization, the first thing that we have to look for is, do we have an acidic or basic functional group? Because this is going to determine what kind of equation we need to set up. The acidic functional groups are carboxylic acids, phenols, like the name of the drug and pKa. Yeah, we'll talk about that as well. Imids and finally sulfonamides. Yes. Yep. As soon as, so it takes about 20 minutes for it to configure, and then I upload it to YouTube, which is like another 10 minutes. So I have some work I need to get done tonight, so I'll be able to upload it as soon as it's ready. Yes. Okay. So we have our 4 acidic functional groups. All of these acidic functional groups have acidic hydrogens on them. Oop, I forgot to draw the one on the imid. All of them have acidic hydrogens. So what this means is that we have our acid, our drug structure, and in its neutral state, it has that hydrogen on it. No worries. Would people want to take like a 5-minute, 10-minute break before we keep going, or just go straight through it? I should ask. Break? Okay, we'll take a break. Yeah. I a break would be good for me as well. All right, let's come back at like 9:21. We'll do that, and then we'll continue. It's going to be posted to the classroom. If you don't have the Anna, are you on the classroom? Get back into it. So before the break, what we identified all the acidic portions of these structures. And so generally what happens is that you have the acid with its hydrogen attached. And what will happen is that that acid will donate its hydrogen to the solution. I need more colors. So we go from neutral to negative with acids. Acids go neutral to negative. When so what I want you to know is that if you have one of these structures given to you, you know your drug is acidic. But what happens if you were just given the name of the drug? How do you figure out if it's an acidic or it's a basic drug? So for example, if you have phenytoin sodium, acidic or basic drug. The way that we figure this out is based on the conjugating salt. So we know that sodium is Na. What is the general charge we find on sodium? Positive or minus? Positive. So if we have positive sodium, this must be conjugated with negative phenytoin, which, what kind of drug is negative? Acidic drugs. So acidic drugs are usually conjugated with a positive salt. So if you see a drug name that has sodium, potassium, I don't know why you would ever use it, but lithium or calcium, magnesium, all of these are indicative of an acidic drug. Why? Because they are all positive counterions and they would conjugate with a negative acidic drug. Does that make sense so far? Okay, sweet. Your conjugate, basically conjugate is just the thing it's connected to. Conjugate is a fancy term to mean that you have your positive counterion connected to your negative drug. That's a good question. All right, basic functional groups. Oop, I don't want to use green. Our basic functional groups are things like amines, like NH2, or we could have a secondary amine, primary, secondary. We can also have pyridine, which you guys should definitely be able to draw the structure of. And we also have, similar to pyridine, we have aniline, which is a benzene ring, but the nitrogen is above the benzene ring, or coming off of it, I should say. And if you have a basic functional group, what is going on here is that you have your base hanging around, and it comes in contact with the solution. It comes in contact with the solution. Bases love picking up extra hydrogens, and so we end up with our protonated base. And notice the charge on the base. We went from neutral to positive. So in the similar way that if you had what am I trying to say here? If you had a drug name, like we can go back to our good old friend imipramine. And often you will see imipramine with a counterion of hydrochloric acid. Hydrochloric acid is primarily focused on the Cl, which is negative. So what we have going on is we have really Cl minus conjugated or connected with imipramine, which in order for this to happen, imipramine must be positive. And so this tells us that if you have a group like HCl, HBr, HI, or I think as well, does he talk about? Or if you see something like sulfate, nitrate, all of these are indicative of a basic drug. So the counterions for a basic drug are the halogens, sulfate, and nitrate. Is that clear so far? All right. So let's talk about how we find percent ionization. So step one was identifying, is it an acidic or basic drug? We have two ways of doing that. One is with the structure, the other is based on the name. And specifically, we care about these equations because that's going to come into handy when we talk about what kind of, if it's protonated or unprotonated. Let's say that we are talking about phenytoin sodium, which has a pKa of, I don't know, 2.3 at a pH of 7.4. And the question that I want to know is, will it be protonated or unprotonated? First steps first, like we did up above, is identifying what kind of drug this is. So we know that this is a positive counterion, which means that this must be an acidic drug. Step two is we are going to choose the corresponding equation. So we can either have the acid equation, or we can have the base equation. So once we identified what kind of drug it is, we know that we're going to be choosing the acid equation. So here we have phenytoin, which would have its hydrogen connected to it. And we know that it can dissociate into negative phenytoin and H+. What's important to know is that we should be able to identify right now which of these two structures is the protonated form and the deprotonated form. So label protonated and deprotonated forms. So on the left, our drug has a hydrogen, so this would be the protonated form. And when the drug loses the hydrogen, this would be deprotonated. once we figure out that, we're going to label the protonated drug with the pKa, and we're going to label the deprotonated drug, and we're going to label the H plus with the pH. So for our drug, we would put pKa over on the left-hand side, and we would put pH over on the right-hand side. Then we're going to use Mother Nature's rule. Mother Nature, MN, big MN herself, will always choose the weaker acid, which in this case means the higher number. So, in terms of our drug, which one is going to be chosen? Well, Mother Nature will always choose the weaker acid, which in this case is 7.4. So at a pH of 7.4, phenytoin is going to be deprotonated. Any questions about this so far? All right. Now the question becomes, how deprotonated? Or in other words, how ionized, right? Because in the same way that a protonated drug is neutral, we can also say that it is deionized. And the same way that a deprotonated drug is negative, we can say that it's ionized. So we're going to construct our number line. So we would have 0 all the way up to 14. And we can label in our pKa of 2.3. And we are going to label in our pH, 7.4. This thing would probably be further down. And what we can do now is we can look at, we know that based on what we said earlier, that as we go from our pKa towards our pH, we become more ionized. So as you go from the pKa to the pH, we become more ionized. How did we figure that out? Mother Nature told us. So I can put that in red just so we can see how that came about. What we can say here is that now we're going to move up the number line by 1 pH at a time. So we have 3.3, then we have 4.3, and then we have 5.3. And what each one of these steps correlates to is that ratio of ionized to unionized or non-ionized. So for the first step, we have 10 over 1. For the second step, we have 100 over 1. And for the second step, we have 1,000 over 1. And then we know that we can do that math that helps us tell what the answer should be. So we know that 7.4 is above the highest step we have. So that means it would be above 1,000, above 1,000 over 1,001. Well, we could fill in 6.3, 10,000 over 1, but usually you're only going 3 steps at a time. And you'll see why in a second. Because we know that if we divide 1,000 by 1,001, divided by 1,001, we get 99.9. So at 7.4, we are going to be more than 99.9 ionized. So the math tells us the number. The diagram tells us what kind of structure we have. Good question. We always go 3. We always talk about 3 positions because if I did a 4th position, it would be 10,000 over 1, which would be 99.999, which at that point, you're basically saying 100%. The reason why we talk about 1,001 is because what this 1,000 represents is 1,000 ionized molecules for every 1 non-ionized. So it's like in a bag, we have 1,000 ionized and 1 that isn't. But if I want to take an average of them, I would have to add them both together to get my denominator. Does that make sense? So it's 1,001 because we're adding the denominator and the numerator. So let's take a look at another example. This will get easier with practice. Also, there are places, I'm not going to tell you where, but there are places where you can speed this up and it doesn't have to take so long, but it comes with practice. So let's say that we're talking about citalopram hydrochloride, which has a pKa of 11.3 No, that's way too high. We'll say pKa of 8.6 at a pH of 6.8. First steps first, acidic or basic? It's a basic drug. Exactly. Hydrochloride tells us it's basic. Step 2, we choose the equation. Which, if you flip back to your notes, would be this guy, citalopram plus H plus becomes citalopram with the hydrogen and a positive charge. So if you're wondering where that came from, it came from that step. Once we come up with this, we can label the deprotonated and the protonated side. So we're going to label the protonated and deprotonated. So which side is the protonated side? The left or the right? Which side is the protonated side? The left or the right? So the protonated is the one where we have the drug that is physically connected to the hydrogen. So in this case, here's my protonated side, which means this is my deprotonated drug. We could also fill in, if we really wanted to, we could say that this is my non-ionized drug, and this is my ionized drug. How do I know this? Because my ionized will always be positive. My non-ionized will be neutral. Step 4. Is we're going to label the protonated drug with pKa and label the H plus. So pKa will always get written below the protonated drug. So this goes to the protonated drug. And pH will always follow the H plus. And then we follow Mother Nature's rule, where we choose the weaker acid, which is the larger number. So who is the weaker acid? The protonated drug or the deprotonated drug? The protonated drug. So Mother Nature is going to choose the protonated drug. Now we can take a look at our number line. So we can say that we have 0. Wow, I can't draw in straight lines. All the way up to 14. We can add in our pKa at 8.6. And we can add in our, I did this in pink, pKa 0.6. We can add in our pH, which is at 6.8. And we know, based on what we set up above, that as we go towards the pH, what kind of drug is preferred? Protonated or deprotonated? What kind of drug is preferred based on what Mother Nature told us? Protonated, right? Which means Mother Nature is choosing ionized or non-ionized. Is Mother Nature choosing ionized or non-ionized? Ionized. Exactly. So Mother Nature is telling us what kind of structure we should have. Now we just need to figure out the percent. So we can say that we have 7.6. We have 6.6. And we have 5.6. So at 7.6, we're going to have 10 over 1. At 6.6, we're going to have 100 over 1. And at 5.6, we're going to have 1,000 over 1. So 10 over 1 would be 10 over 11, because we take the total amount of parts we have. So we have 11 parts total, which would give us, so we have 10 divided by 11, which is 90.9. And then we have 100 over 101, which is 99%. And what we see is that our pH falls in between those two numbers. So we can say that we know that at a pH of 6.8, we are 90.9 to 99% ionized. Does this process make sense? Any questions about this process? Could we have done also 1,000 to 1? You could, but generally what we do is we pick the two numbers that it would fall in between of. Right. So we can see that 6.8 falls in between these two positions. So it would make sense to choose those. Because otherwise it would be 90 to 99.9. It'd be too big. If Mother Nature chooses the weaker acid, why is the arrow in the line pointing backwards? It's pointing forwards. We have the forward arrow and the backwards arrow.
Oh, I meant on the like the 0 to 14. Why is it pointing to?
Oh, because this is showing, we know that the drug would normally be at 8.6, but it's moving towards the pH at 6.8.
Okay.
Does that make sense?
Yeah.
Okay. Does this process standardize and give you a way of accomplishing this problem? That was the big thing that I wanted to develop, was steps to give you guys. Okay. All right. Should we do a practice problem together? All right. So I'm going to give you mm, You can have scrap paper. I believe you can have scrap paper on the exam, and then the software, the test software, has a calculator in it, so you won't need so you don't need to bring your own. Yeah. pKa equals, I don't know, let's say 5.4, and I want you to tell me what is happening at a pH of pH of 8.1. Well, technically you don't really need to, because the ratios are always going to be the same. 10 over 1 is 90%, 100 over 1 is 99%, 1000 over 1. So technically you don't really need a calculator there. All right. And then while you guys are doing this, I'm going to come up with the answers. So is it gonna give you one more minute. Take care. All right. Let's go through this together. just so we can talk through it, and then we'll be all set for tonight. So here we have a drug, and we have this HBr that's included. And this is a really, really big clue that we are talking about a basic drug, right? So we have we can also identify this based on the fact that we have an amine, which we know is a basic functional group. So what we have going on here is we have a basic drug, which would follow the formula of drug plus H plus becomes drug H positive. We can say that this is the deprotonated side, and here is the protonated side. And we can also label this and say that we have the ionized form of the drug and the non-ionized form of the drug. Next, we're going to label where the pKa is, which would always follow the protonated form of the drug. And then we label pH where H plus is. Any questions up until this point? All right. Mother Nature will always choose the weaker acid, which in this case would be 8.1 because it is the higher number. So at a pH of 8.1, what form of the drug is going to be preferred? Non-ionized. We can go to our number line. Zero to 14. We can plug in a pH of 5.4 and then fill in 6.4, 7.4, 7.8, 7.4, 8.4. And we can also plug in where the pH is at 8.1. So at 6.4, we'd have 10 over 1. At 7.4, we'd have 100 over 1. At 8.4, we'd have 1,000 over 1. So our drug falls in between 100 over 1 and 1,000 over 1. So 100 divided by 101 would give us 99%. And 1,000 divided by 1,001 will give us 99.9%. And what form of the drug is this? Is it 99% ionized or 99% non-ionized? Non-ionized, exactly. And again, we got this because Mother Nature is telling us what form of the drug is going to be true. So of our options up here, we have 99 to 99.9% non-ionized. Which one is the correct answer? Which is the best answer, I should say. A, B, any other ideas? B, wait, B. So the answer here would be B. Why is it B? Because in the same way that we can say that we have 99 to 99% to 100% non-ionized, the opposite of this would be 0 to 1% ionized. So the answer here would be B, because it's not that we have almost 100% of the ion form. So here we're taking the opposite of what the Mother Nature told us. Like we're looking at the reverse, right? So this is why it's very, very, very important to specify what you are looking at down here, right? This is what Mother Nature told us. She told us that she prefers non-ionized. So we either need to look for this range in the answers or the opposite of the range. Does that make sense? Very sneaky, very tricky. But I wanted to give you guys an example because this is probably how it's going to get phrased on the exam. And I don't want you to get tripped up. When we did the acidic, we went from pKa to pH. In the same way, you know, here, if we draw an arrow, we can say that we're going from pKa to pH, which would be going towards non-ionized. So again, the arrow shows the direction that we're moving, but where this came from is based on what Mother Nature told us. Does that make sense? No problem. Any other questions? Does this make this process much easier? That's like the big thing I want to know, because I sat down today trying to like figure out a way to explain this and like come up with steps and different stuff. But okay, great, 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 great. If you want to practice this, okay, come up with a random drug, make it acidic or basic, and then what you're going to do is online, just have a random number generator between 0 and 14. There's your pKa, there's your pH, and just practice going back and forth, right? That's all you need to do to practice. Assign if the drug is acidic or basic, and then give yourself 2 random pKa, pH numbers. That's all you would need. I'm sure there's a number generator somewhere that, you know, you can give yourself decimals if you really want as well. Yeah. The notes, meaning like the drawings. I believe I can. The problem is that sometimes it comes out like this, and it kind of, this is what I imagine like the inside of Mahana's brain looks like. So I will see if I can get it to post. But yes. If not, I will just send you the file and then the software to open it, and then you can do it yourself if you want. No problem. All right. That is where we